There are a couple of quick questions which we can briefly discuss before I jump back into my topic. Okay. So one is regarding flow suppression and attachment. So of course, I mean, Professor Das has actually explained to you in good detail, but if I see there is some confusion. So the flow suppression is simply because of adverse pressure gradient. So what happens, I mean, when I take an airfoil, no, yeah, I can take this. So imagine this airfoil, you can see the cross section of this guy, it's an airfoil, right? So this airfoil, if I continue to increasing the angle of attack, okay, you end up getting higher and higher pressure gradient. So the way the pressure changes. So if your gradient of pressure is too high because of the high angle of attack, the flow cannot actually continue to remain attached to the surface of the airfoil. So it will separate. Even other times, I mean, even when, I mean, sometimes your angle of attack may not be that high, but something else can actually cause adverse pressure gradient, or it can actually try to sort of disturb the flow, causing a separation. So such things are, for example, shock wave. So if the flow over the airfoil actually becomes supersonic, your actual, I mean, the ambient flow may not be supersonic. So your ambient flow or the free stream flow may still be subsonic. It may still be less than speed of sound. But the moment it actually goes over the airfoil, because of the acceleration it actually ends up getting in the beginning, the speed may actually momentarily go over Mach 1. This would actually cause setup of some weak shocks, and these weak shocks may also cause flow suppression. So now, once this agent which is causing this adverse pressure gradient or jump in pressure which causes the suppression, if that agent is removed, the flow may reattach. So normally what happens, when my angle of attack I reduce, the adverse gradient goes away and the flow will reattach. And if my airfoil is actually undergoing dynamic motion, like the way it happens in helicopter rotor blades, in that case, this dynamic motion can actually cause reattachment and separation multiple times. So your flow may separate, it will reattach, it will separate again, because the flow is dynamically oscillating or moving up and down and doing all kinds of things. So such scenarios may lead to a phenomena called dynamic stall. Now again, this is not the right time for you to learn dynamic stall. You can study about it, I mean, either in helicopter course, or you can study about it in unsteady aerodynamics course.
So when the flow is actually separated from the airfoil, then what happens? What is there in between that region between the airfoil and the?
So there is still flow, okay, but the flow is no longer, I mean, nice and laminar. So if you remember the animations or other flow visualization videos I showed in the first lecture, and Professor Das also showed some of those. In that, I mean, if you see, when the flow is nicely attached, it is nice and laminar. But once it separates, it will actually start to oscillate and fluctuate a lot. So there is flow. It's not like the flow has disappeared, right? I mean, flow has to be still there, but it's no longer organized and smooth. It becomes chaotic. It becomes turbulent. So there is a lot of mixing happening there, and it's no longer nice. So what happens when there is a lot of mixing and disturbance happening? It will lose a lot of energy. And that's why this kind of flows are lossy flows. So it causes energy loss, and you would actually end up consuming more drag. And it's no longer, I mean, good. You lose lift and you end up incurring more drag. Fine.
Yes.
Right. So, all right. So, other question is regarding how to calculate pitching moment about aerodynamic center and finding the aerodynamic center itself. Well, all this will be covered in good detail in your aerodynamics 1. See, to find the center of pressure, you need to know the pressure distribution. So, center of pressure is just like, I mean, finding out your center of mass. I mean, all of you would have by now learned about finding out center of mass. So if your mass distribution is given to you and the geometry is known to you, you simply integrate and find that. The center of pressure is similar. I actually have to integrate it. So I define my coordinate system and try to find out, I mean, where the effective center is going to be, the way you find center of mass. So similar integrals will be applicable in finding out the center of pressure. And once you know center of pressure, I mean, you can also try to find out the point about which your pitching moment is minimum and so on. So you'll be able to find out aerodynamic center also. So don't worry too much about this. All this will be covered. I mean, these things are not really supposed to be part of this course. this course is supposed to be a fun course where you get to know about different aspects of aerospace engineering. Okay? So the technical details will be covered in corresponding detailed courses. For example, aerodynamics 1, where you will learn about all these things in good detail. All right, so let us jump back. So you can see my screen.
Yes.
So last time when we were talking about various VTOL platforms. So we looked at Lilium Jet, we looked at EHang's design. So let's see some more designs. For example, this is one from Vahana. It's called Vahana rather. It's from Airbus helicopters. So Airbus actually is also putting a lot of effort towards this urban air mobility. So the terminology used is UAM, urban air mobility, where the goal is to develop small personal aerial vehicles or air taxi systems which would be able to carry 4 to 6 passengers typically. So towards that end, they had developed this concept called Vahana. That is right. So the name actually is in Sanskrit Vahana because Germans have a lot of fascination for Sanskrit. I don't know if you guys are aware, Hitler's right-hand man or left-hand man, Himmler, there was a guy called Himmler, he used to carry Bhagavad Gita with him. And there are famous quotes from people like Oppenheimer, Einstein, and a lot of German people also, okay, because they used to study Sanskrit and things like that. So I did try to find out because several of my friends were there in Airbus USA, where they were actually working on this Vahana project. But I mean, yeah, they also could not trace out the origin of the name Vahana. It's an all-electric vehicle, which is a tandem wing configuration. Tandem wing means front and back. So there is one wing in front, another wing in the back. Each of these wings actually have 8 rotors in total, powered by 8 motors. So this is actually an older video. Okay, I should have updated the video to newer one. Okay, let me just quickly pull out the newer video for one moment, which actually shows the forward flight and transition also. I forgot to update it here. One moment. So that's the new video. I just copy paste it here. Right. My screen is still visible to everyone?
Yes, sir.
Right. So here you will see Vahana taking off. So this project is already closed, by the way. Okay. Airbus objective was to study this new vehicle concept. So they built this, they flew it. And after that, I mean, they have shut this project down. It's over. Now they are working on some other concepts. Whether they are coming up with a bigger version of this or something, I am not sure. This was actually a single-seater proof. It was sort of a POC vehicle, proof of concept vehicle. So in this, I mean, you only see it transitioning partially. It's not actually, you see it's still flying like a multi-rotor, more or less, because the wings are not fully tilted. So this is actually a tilt wing concept. So earlier in my slides, I showed you that tilt wings were developed as early as 1960s, but none of them were successful. But this guy has come very close to being successful because it can do full transition and everything. And now, I mean, it is quite obvious because the technology has matured in a significant way. I mean, no longer you are using engines which are there in the, you have lightweight motors and you have these propellers which has variable pitch. So you can imagine this particular aerial vehicle has extremely large number of control surfaces or control inputs. So you have RPM of 8 rotors, which you can control. You have pitch of these 8 propellers, which you can control. So you have 16. You have 4 sets of, I think there are some ailerons also. Or if not ailerons, I mean, I have actually option to tilt the control, change the amount of tilt that is required. So by that, I mean, logic, you have another 2 set of inputs. If I assume that both sides of my wings are actually tilting by same amount. And they would definitely have, yes, they have control surfaces, as you can see on the rear wing and even in front wing. So you have, you can black and red things which you're seeing. These are actually your ailerons or elevators, whichever way you want to use them. So these control surfaces are also there actually on these. So 4 more inputs there. So you have 20 plus 2 tilting angle. So your total of 22 control inputs are possible, which you can use to fly the vehicle. So you can now imagine, I mean, normally in a conventional aerial vehicle, a pilot actually controls, I mean, ailerons which are moved in a particular manner, elevator in another manner. So he can manually control all these things because there are only finite number of these, and so he has 2 hands, 2 legs. So with that, he can easily manipulate 3 sets of controls. But now here, I mean, you have so many different inputs, it is impossible for him to control it on his own. But good part is that this vehicle doesn't require a pilot. It's autonomous and it is flown through an autopilot which is on board. An autopilot can actually handle all this. I'll show you an example of our own vehicle, which actually also has a total of 8 plus 4, 12. Yes. So we have 12 inputs which are going into the vehicle. Yeah. So we'll look at that also. So this is the Vahana, what Airbus developed, a tilt wing concept, which looks quite promising and seems like a good idea to build for a vehicle. Yes. Another important thing you have to see is that the biggest concern when people started developing these tilt wing designs was that when my vehicle is like this, so imagine your wing is like this. You can see my this small model biplane.
Yes, sir. Yes, sir.
So when I actually start flying, right? So when I start take off, I'm hovering, and from hover now I actually want to transition and go into forward flight. So normally, if I start moving like this, right? Okay, what is the angle of attack of my wing if my vehicle starts moving like this?
90.
Exactly, 90 degrees. So that was the concern, right? So you see, Vahana also has same kind of thing. I mean, you tilt the wings. Here we tilt the whole vehicle. We don't actually tilt the wings. We tilt the vehicle, and it goes like this. So initially, when I start moving, so the moment I start tilting this, it will start moving like this, right? Okay. So my angle of attack will be very, very high. So my wings will not become effective for a long time. This is not a good thing. So how do I address that? By having this kind of propellers which are distributed across the whole wing. So you can see very clearly the entire wing span is practically covered by these propellers. So what happens now? These propellers have significant amount of downwash. And in the remaining lectures, we will actually see how to calculate this downwash. That is the flow which the rotor is inducing and pushing it downwards. So this downwash actually is going over the wing. And as a result, even when it is hovering, the angle of attack on the wing is what? What is the angle of attack going to be when my vehicle is hovering and the entire wing is covered with the downwash coming from the propellers?
Angle of attack would still be 90.
I cannot hear you. Are you speaking Sanskriti?
Yes, sir. So
Your voice is coming too low. Bring the mic close to you.
Hello.
Or yeah.
Yeah. So sir, even if it is like hovering, so then also the angle of attack would still be 90, right?
Still be 90, you're saying?
Sir,
Yes, sir.
sir, is it moving upwards or it is moving in
It's
when the
not moving
plane?
anywhere. It is actually standing still. It's just hovering.
Then it will
There
be
is-
0, I think.
It will be 0 exactly.
Propellers
Zero.
are sending downward.
Exactly. So it will be 0. So in normal, even when I start moving, okay, what happens? My prop wash is very high. Prop wash may be 5 meters per second. My vehicle may start moving only like 1 meter per second, 2 meters per second. So initially when I'm moving and also pitching, right? So my vehicle will be pitching continuously. Or in case of Vahana, it is actually the wings are tilting continuously. So when you start moving, the angle of attack will still remain very small. So that is the whole trick. So if I have this kind of distributed propulsion system, it actually allows your transition process to become very, very easy. Because prop wash would ensure that your angle of attack always remains small and wings become effective very, very quickly. And I'll show you, I mean, like our biplane tail seater, it actually moves very fast. It transitions, I mean, almost instantaneously, as you will see. So now we looked at the video from Aerovelo, right? Aerovelo team, which actually flew that human-powered helicopter. So, I mean, I heard that somebody told me that the entire Aerovelo team, one of my friends in US, he told me, I was meeting him during one conference. He told me that this entire Aerovelo team was actually hired by Larry Page for his personal company called Kitty Hawk. So Kitty Hawk is not a Google company. It's not owned by Google or Alphabet. It is actually from personal funds of Larry Page. So they made this crappy looking, absolutely horrendous, atrocious vehicle. Everybody made big fun of these guys. Okay, when they ended up making this, so they will fly this. Nevertheless, well, flying is good, but otherwise, I mean, it's not really a good design by any means. Nevertheless, they went ahead with this. They made it better. So all of you remember the name Kitty Hawk, right?
Yes, sir.
Because that's the place from where Wright brothers took off. All right, so this is one boring video. Now we'll move on to the flyer, okay, which they.
My only dream from my childhood, I remember, was when I could fly, and that was such an amazing feeling.
I mean, an improved version of that crappy design. This is a better version.
Very few of us.
So that is Sebastian Thrun. Yeah, this guy is Sebastian Thrun, he is CEO of Kitty Hawk. So they made this vehicle flyer. They made another vehicle called Cora. That is more towards air taxi. The flyer actually is already operating, I mean, somewhere near Bay Area where they fly it over some lake or something. So you can go and rent it, pay some money and get to fly this flyer.
This is an amazing moment. Just in the past 2 years, so
this is Cora.
Because
I mean, again, it's not a very exciting design for me. I mean, as a aerospace engineer, because what they have done is that they have just attached a multi-rotor to a fixed-wing airplane, and that's what a lot of people are doing, and I don't like that at all, actually. So you see, it has, I mean, 3, 3, 6, 6, 12, some 12 small propellers. Small propellers are not good, which are actually fitted onto this vehicle. I mean, you can imagine when the airplane flies forward, all this will be actually sitting in air, accumulating huge amount of drag. So this is a simple concept, but not necessarily the most efficient concept. Now, some of my friends actually have even joined Kitty Hawk. Anyway, so that's a different thing.
Has a range of 100 kilometers. And unlike cars on the road, it travels in a straight line. And it will never have to stop at traffic.
So that's the idea. Cora, a vehicle which has a lot of people are making a lot of drama. Yeah, so you can take off and land vertically with this propellers, 12 of them actually, and you switch them off and use the propeller for forward flight. Now they did not get permission to fly in America, so they actually did their test flights in New Zealand. I think New Zealand is like safe haven for everyone because they have very liberal aerial vehicle rules. Okay, and as a result, I mean, a lot of people go to New Zealand to test their prototypes and concepts and so on. So that is Cora from Kitty Hawk. Now I'll show you yet another vehicle. So Larry Page actually is supporting two companies, Kitty Hawk, and the other company is called Opener. And this company Opener has made this quite remarkable. So this is a quite interesting vehicle. Again, I mean, not necessarily the best possible solution out there, but it's very remarkable and quite exciting vehicle there. So check out Blackfly. And I have a strong suspicion this is also flown in New Zealand. That is a Blackfly. So the design actually is again a tandem wing design with distributed propulsion. You can see they are also using 8 propellers. The wings are of low aspect ratio, and they have put some winglets to improve the efficiency. Okay. But it's not actually a tilt rotor or a tilt wing. This actually is close to being a tail sitter, but almost half tail sitter, in the sense that the vehicle has actually body which is the bottom of that is actually made like a boat. So it can do landing on water, and it can actually do a rocking takeoff. So it will sort of rock on its back and take off. So when it's hovering, actually the person who is sitting inside, he's actually leaning backwards, almost like this. So he's leaning backwards. So you can see this guy also, he's seeing from backside because the entire vehicle is tilted. So that is slightly inconvenient. To do forward flight, the vehicle will pitch by 45 degrees almost. This is forward flight. In forward flight, both your wings are in different planes. Once you are going in forward flight, you can see both the wings actually are in different planes. So when it is hovering, it's actually making use of its ailerons, as you could see. And that's how it lands on the belly. So you see, when it comes to land, it actually has very high hooks like that. It has actually pretty high inclination, right? So the person is almost leaning on his back, all the way back. And then the vehicle walks back forward. So it's a nice, unique, interesting design, actually, I have to say. No moving parts. Tail sitters actually have this advantage. No moving parts. You don't require tilting of wings or things like that. So that was Blackfly from Opener. So I'll now talk a bit about, before we go into more technical details, I thought I'll show you different things, because yesterday all of you were, or rather in the previous class, you are all very curious about, different activities that goes on in IIT Kanpur. Okay. So I can talk about what I do, and my colleagues do. Me and Dr. Kothari, we work together on most of the things because we have complementary technical skills and we partner in a lot of things we do. This is our unmanned helicopter, which we have been developing for quite some time. It's now close to being a product. This is a slightly older video where we showcase various features of this unmanned helicopter. It can do auto takeoff, auto landing. It can hover very precisely. It can do autonomous waypoint navigation, where you set the parameters and you fly on its own. So this part of the clip is actually from our flight test, which we conducted in Ladakh at altitude of 11,500 feet. And the vehicle performed very well there. Of course, because it's an engine-powered vehicle, the performance actually degrades, because at that kind of altitude, your density is significantly low compared to what we are used to at sea level or at lower altitudes. So some of our students have been working on this robust autopilot, which allows this helicopter to fly upside down or do aggressive maneuvers. The reason we developed this kind of robust autopilot is that because when you're flying in extremely challenging environments where there is a lot of wind, so these small unmanned aerial vehicles are actually susceptible to wind. So wind can actually toss you upside down. You cannot do anything about that. So that's why we worked on developing this autopilot, which can handle such kind of disturbances and still be able to come back to its original orientation. Apart from that, we also worked on this auto rotation, right? We have been talking about auto rotation, how helicopters are unique vehicle, and before them, auto gyros could actually switch off their engines or turn off their power, and they could land safely and come down in a controlled manner. So one of your seniors who did his bachelor's, master's, and then he did PhD also with me. So he's a dual and then PhD from IIT Kanpur. He developed this autopilot, where the helicopter can, the same helicopter which you are seeing, can do an auto landing in the event of power failure. So this actually builds in the safety. Say my engine somehow switches off because of some problem, there is some malfunction, or my battery runs out for the main power plant. I can still actually come down and land in a controlled manner, as you will see in this particular video. So vehicle can come. So this is actually vertical auto rotation, but at the same time we can do even horizontal or forward flight based auto rotation, which is even smoother when it comes to land. That is the auto landing part happening. Apart from that, I mean, we have integrated winches at one point of time for it to pick up cargo and drop it in a controlled manner. It goes to some destination and then it will come down and drop it, and so it actually even has the mechanism to release the package remotely itself. So without requiring any human intervention and so on. So that is, so we had done, I mean, all kinds of research. We had developed flight simulators, we had developed hardware and loop simulators for this. We had done, explored the design in various manners. We have done fabrication, manufacturing, optimizing the whole design, looking at how to minimize the drag. So this is very applied kind of work where all the knowledge that you acquire during your BTech courses, all that actually comes in handy to sort of work towards developing it as a product. Right now, we still have an unsolved problem. We are trying to see how to minimize the noise from the engine, because these are two-stroke engines. They are very, very noisy. The silencer which is there is, I mean, for the namesake, it doesn't do much work. So we are trying to collaborate with some of our colleagues in mechanical who are trying to design a nice muffler for it, which will actually be able to reduce the noise without compromising the power output from the engine. This is more detail about the this auto rotation thing. Okay, so here you can see it clearly braking, right? Okay, so we switch off the engine. I'll turn on the audio so that you can hear the change in sound of the rotor. So the moment we turn off the motor, you can hear that the motor sound goes away. This is a very complicated problem actually. We had to apply even artificial intelligence. We even made use of careful testing, and then did a lot of simulation to first. So even before we actually tested on the real helicopter, we tested the entire process in our simulator. Because if you make a mistake here, your entire helicopter worth several lakhs of rupees will actually be gone. So this work was done by Sagar. Okay, so Sagar now actually is an entrepreneur. He is working in Singapore. He has his own startup there actually. Not in aerospace, but in some other domain which he had more interest in actually. Then in 2018, we actually came across a competition in America where there is an organization called National Institute of Standards and Technology, NIST, which is a government entity, actually a lab supported by, so it's a lab supported by Department of Commerce in USA. So they had a competition going on where the goal was to design a helicopter which can lift 10 kg payload and hover for more than 1 hour or so. So we formed a team for that. It had various people, several PhD students, master students, and BTech students. And in 3 months' time, we designed, built, and fabricated this unmanned helicopter which can lift 10 kilogram payload. So it still sits in my lab. Unfortunately, we have not gotten enough time to develop it into a product. But after we are done selling enough of our current products, we'll definitely revisit this and try to perfect it. Right now, it's more like an experimental prototype, which requires some refinements to make it more reliable and robust to work with. So the whole design required all the knowledge for helicopter technology. The whole transmission was designed here. We got it fabricated mostly in Kanpur. Even the autopilot was developed here. So effectively, this particular small helicopter is India's first. I'm sorry. So this is India's first tandem rotor helicopter. These days now, I mean, Indian Air Force actually has bought the Chinook helicopters. Yeah. Exactly, looks like Chinook, right? So Chinook helicopters have been bought by Indian Air Force, but they have come very recently. I think in 2019 or 2020, it got delivered. So this was the first tandem rotor helicopter flying in India before Air Force bought their own helicopters, right? So this is one of the first flight tests which we performed on this to check how it is handling, how the roll, pitch, other controls are actually. Okay. So in this this design actually was the top 3 design in the entire competition, and we got $20,000 for making this design. Then we have also developed this engine powered quad rotor. Okay. Now, I mean, there are 2 ways of making an engine powered quad rotor. I can have an onboard generator, or I can have a transmission system which actually controls all the 4 rotors directly. So we followed the latter approach and developed this particular platform. This was actually a DRDO project. DRDO had interest in this kind of vehicle, so we developed it for them. Even the helicopter project, actually, this helicopter project actually has been funded by DRDO, has been funded by Department of Science and Technology, different aspects of it. So several people actually or several funding agencies have contributed towards its realization into a product. Now comes the tail setter design, which I was having. So this is a small replica of this same platform. It has 2 wings, and then either you have 4 rotors or you have 8 rotors. So in the current, this particular video, you will see 4 rotor version. Okay, this is still flown somewhat manually, but then I'll show you the product form of this. So this was actually a research prototype, which we developed a few years back, and we use it for control law development, checking the controller and checking out some other design features and so on. So in this, you will see it taking off, takes off vertically. Like a normal quad rotor. And then the entire vehicle will actually turn by 90 degrees. And you can see it actually happens very, very fast in a fraction of a second. So it takes off, and then just turns by 90 degrees. I mean, that dramatically you could see, right? And now it's like a biplane airplane. But there is a difference between what Wright brothers had. There is no tail. You don't have a conventional tail. There is no elevator. There is no aileron. I mean, yes, ailerons are there. Sorry, there is no elevator. There is no vertical tail either. So it's a tailless airplane. So inherently it is unstable. But because there is an autopilot sitting on board, that makes the vehicle very easy to fly, controllable, and even autonomous. So we have done a lot of work on this. We have done wind-tunnel tests to characterize the performance. We have done flight simulations for this. We have done design studies on this. We have done propeller design for this, and we are still doing a lot of work on this actually to improve it. We have to optimize the wing profiles, look at the spacing, how we absolutely yaw is definitely possible actually. So because we have 2 sets of propellers, if I need to yaw, I can increase thrust on these 2 guys and I can decrease thrust on these 2 guys. So it can yaw very nicely. So it's a different way of doing yaw. You don't require to deflect a wing, a vertical wing at the back, right? Like normally you have. So, I mean, you can see it is doing turning flight all the time, right? So how it is yawing? So it can do nice controlled turns actually. So now you can see how it does back transition, which is also almost instantaneous. You see just at almost full speed, actually it turns back and becomes goes back to the hovering mode. Not exactly. The yaw in normal quad rotor drones is done through torque imbalance. Here we actually give a thrust imbalance. So 2 rotors have higher thrust, other 2 rotors have lower thrust. So it's yawing through that. So you create a moment between the 2 thrust vectors from 2 sets of propellers. So it's not quite like that in normal quad rotor. So when it is hovering and you try to yaw, okay, and if you try to yaw using the torque reaction, you will see it will be very sluggish. So we have put these ailerons, which actually works like a vane, a yawing vane, which allows you to do pretty fast yaw motions. So now this is the video where you see it doing the manual flight. Now I will show you the video of this developed version. So now this whole experimental concept has been converted into a product. which my startup is already selling. It's called Orbit. This is our flight hangar. So as you saw, and this entire vehicle has been actually designed, built, and fabricated in my lab. Okay, right here. So where I'm sitting, I mean, just downstairs. I mean, this entire thing has been built. Okay. So, right. So apart from this concept, I mean, there are other designs also we have been working on. We have had this concept of air taxi system, a single-seater personal aerial vehicle kind of thing, which we did for Vertical Flight Society design competition. So I also teach this course on UAV as well as a course on helicopter design, through which, I mean, we tend to participate in the competition that is organized by Vertical Flight Society. So every year they have some new problem. So depending on the interest of students. So if we have enough number of students who are interested to take it up, we participate in these competitions. And 1 year we won third prize also globally for designing a helicopter which could actually hover continuously for 24 hours. So that was a very unique design and unique problem. That project was also sponsored or supported by Sikorsky helicopters, which you saw details of, I mean, earlier. So this is one concept. So this is again sort of a tilt wing and morphing wing design concept. So part of the wing and propeller tails, and some of it actually morphs also. So you can see it actually in the morph configuration where it becomes very compact, because there was a critical requirement for the whole system to fit inside a very small narrow area. So we carried out each and every, I mean, the students, I mean, who worked, took the course, they carried out the entire design and development, I mean, themselves. Of course, we are not trying to make anything here. It's all just a concept. Okay. So this is a conceptual design, what is called a conceptual design. Now, I mean, if there is funding, one can actually easily make a small prototype, a proof of concept, and one can go for a bigger funding to realize the full thing, because nobody makes, I mean, a full scale aerial vehicle in one go. Anybody, I mean, even Vahana, I mean, they first made a small remote control prototype, which actually allowed them to test out multiple things before we move to the full scale vehicle. So like that, I mean, you saw the Orbit, which right now can lift 5 kg payload. We are in process of now starting the design and manufacturing for a system which can lift 20 kg payload. And eventually maybe we'll go for 200 kg payload. So that is the goal. So you take steps and you try to make bigger things. So doing all kinds of, I mean, theory, question writing, simulation, experiments, everything is, I mean, everything comes to final, I mean, thing where you actually make a vehicle by learning, by applying all the knowledge that you acquire. So as you will be doing various courses over the next 2.5 years, whatever knowledge you acquire through these multiple courses, all of that, the culmination of all of that comes in when you try to design something. And once your design is realized in an actual real vehicle, and when you see it flying, that's when you realize the power of engineering, and you really feel the joy after all the struggle that you have gone through in designing something and making it work. That's the real fun, actually, and that's what I mean gets me very excited. So here's some more details about, how the internal structure of the whole fuselage was thought about. There are bulkheads, longerons. These are all structural aspects. Because finally the structure has to be designed in the most efficient and optimal manner. A lot of innovations happen there. For example, when Maryland team was trying to build this human-powered helicopter, the requirement to make the whole design ultralight is super critical, because every gram of weight there is going to make a difference of a few seconds in the whole of flight time. So when they made the whole wing, the entire wing was actually made up of, the ribs were made up of, I think, foam kind of thing. And there was a spar which was made up it was made up of balsa wood. And the skin was actually nothing but just plastic sheet to keep it very, very light. And when they designed the airframe, in airframe, they actually built trusses. Now, I'm sure all of you are familiar with trusses by now, right? Yes or no? You have come across trusses. What are trusses? Which are used in construction, in all kinds of, even helicopters, you'd see the tail booms made up of truss kind of structure. Anybody? Yes, no, maybe, not, you don't know. Are you guys there? Okay, there are chat messages. Let me see. You have not heard of truss? Mechanics course in first year, did you not have any mechanics course? No mechanics course. Truss structure. Let me type it. Truss. TRUSS. So truss is actually, okay, fine. Most of you would have been to, somewhat triangle, not just triangle, but if you go to any railway station, and if you look up, okay, the platform area, the shade on the platform area is actually supported through this whole truss kind of structure. On top, they would have put some kind of metallic sheet or something, but the entire weight taking member is actually a truss. It's a space truss, 3-dimensional truss. But the simplest possible truss could be 2-dimensional. I can draw, maybe I can do the quick sketching and explain to you. Because you need to get familiarized with the structural aspects also. Just connect my tablet. One moment. Where is the pen? Okay. So let me use the annotate tool. Right. So a simplest possible truss could be something like this. Okay. Even bridges actually, right? So you would have seen a lot of bridges which actually are supported by these trusses. So these trusses actually have the unidirectional or uniaxial rather, yes. So uniaxial members which can only take tension or compression. So you can imagine these small rods which are connected together. They will all be connected through these pin joints. So all these points will be actually pin joints. Sometimes they may be riveted also. So other times, you may actually put here something and rivet it actually. Okay. So like in platforms or bridges and all, you'll see riveted joints. So they would have this kind of members. It could be a slightly thicker member also. It could even be some different eye-shaped member. So different kind of shapes the members may be used. And through this, you can create this kind of truss kind of structure. Maybe yes. Some of these techniques, RC models, you don't make truss actually so much. Okay. But the point I was trying to make is that, so this is a more conventional truss, okay. 3D trusses would actually have this kind of triangular kind of cross section, for example, and this whole thing will be extruded. Okay? So it will be like this kind of thing. It's sort of like a pyramid, right? I mean, small, elongated pyramid kind of thing. And inside this, you will have these members connecting like this to make it strong and rigid. Okay? So there will be these interlinked members everywhere. Okay? This is like a sort of a 3D truss now. So to make the whole structure of that HPH team in Maryland, they actually made each of these members also a truss structure. So they made these kind of micro trusses, really small, tiny trusses, which actually formed each member. So instead of using a solid member here, they actually made this also a truss structure. So each of these members actually was a truss kind of thing. I'm just making some crude representative drawings, but that's what they did actually. And that made the whole structure very, very light, extremely lightweight, but without sacrificing the strength. So in aerial vehicles, the critical requirement is to how do you make structure as light as possible without actually sacrificing the weight. So this kind of structure is somewhat like that in the sense that it is also can be called a truss kind of thing. But the critical terms are bulkheads. So here you see whatever stronger areas are there, they're called bulkheads. And then this lighter ring kind of structures are called longerons. Sorry, not ring kind of structure. The longerons are actually the rods which are running across the length. These are called longerons. These circular things are actually called stringers. Okay. And then there is a deck created which is for the fuselage, where the individual who will be there will be sitting and all. Okay, this is the breakdown of the whole wing, how there is again rib kind of. So these are called individual airfoil sections are called ribs. So this is similar thing which is used for aero modeling also, but aero modeling has learned from aerospace, right? Not the other way around. And your skin, you may have a Nomex honeycomb inside, or you may actually have different foams. For example, there is a I forget the name of the foam. There are aerospace grade foams which can be used inside wings and rotor blades also. Truss is just a shape, a geometric shape which is created by connecting. Exactly, Google it. I mean, you can see a number of pictures actually for that. So it is just a geometric shape which is created by connecting uniaxial structural members. So you take rods or beams rather and connect them to form geometries, and these geometries will be used to take load or transfer load. Okay, so that's what a truss is. So it's a sort of a building block of structural elements. So yeah, search for this word. I mean, and you will be able to see many things there. Right. So that was some comment about structural aspects. I'll go into the details of structures also, and that will become apparent to you. In future lectures, we'll talk about some structural aspects like load factor, Venn diagram, and some other things like that. And what are the critical aspects which you have to consider when you start the structural design? I guess you have not done the mechanics of solid course right now, right?
No, sir, we haven't done.
Yeah, that is why. So when you do mechanics of solids, you will see a lot of n number of truss problems there. So that is the course which will teach you about that. Then we have also been working on some somewhat esoteric concepts, call them random. So when I was in my second year in BTech in Kharagpur, there was a project which was part of the dynamics course there. The course was actually taught by Professor Amitabh Ghosh, who was director of IIT Kharagpur at that point of time. And he is, I mean, really an amazing teacher. Really amazing. And interestingly, he was a faculty of IIT Kanpur Mechanical Engineering Department. And Professor Ishan Sharma was also taught dynamics by Professor Amitabh Ghosh only. And I guess Professor Ishan Sharma also did some BTech projects with Amitabh Ghosh. So that's a separate story. So in that particular course, the project actually wanted me to make, or wanted groups to make these boomerangs. How many of you are familiar with boomerangs? Raise your hands. How many are familiar with boomerangs? Two, I see only 2 hands. Okay, I see some more hands, around 10 hands. All right, so 13, 14 hands. Now you can bring your hands down. So almost like 10, 15 hands. Now people who have played with boomerangs, you have to raise your hands. Who have actually played with a physical boomerang. 2, 3, 4, 5. So very small number there. So I guess maybe we'll reach 10 eventually. We are at 6 right now. So 6 of you have had the fortune of playing with a boomerang. It's very nice. So I built this boomerang way back then, and it was really nice. I mean, of course, the fabrication was done with help from our aero modeling lab people who actually had balsa wood. So we made it from balsa wood, and we made this nice 180-degree angle. And if I would throw it, it would actually come back if I just take one step. So it would almost trace a circular path. So boomerang has these unique vehicles or unique devices which you throw with a good spin, it will go in a circular or a teardrop kind of trajectory. So we have been trying to build this what we call as a robotic boomerang or a remote control boomerang. See the video here. So this is world's first remote controlled or a robotic boomerang, or you can even call it a powered boomerang. Boomerang which is actually powered by battery. And the moment it takes off, it tends to go in some kind of circular trajectory or near circular trajectory. So the interesting thing about this video is that I am the guy who is piloting this actually. And this was the first flight which we did. And I had absolutely no experience of flying any boomerangs or flying any, I mean, I can fly quadrotors, I can fly helicopters a little bit. But yeah, I mean, this was a completely new idea, and I just purely based on my intuition, I gave some inputs and I could actually keep it in control more or less. And another interesting part about this vehicle is that it actually is inherently stable. It doesn't require any kind of onboard autopilot for normal flying. What application it has, I am not sure right now, but it definitely is a nice hobby and toy stuff. Yeah. So one can use it as a hobby for toy. I even actually have plans of eventually selling this actually as a toy, but too busy right now selling UAVs. So once I have done that, maybe I can switch to this eventually and see if somebody can make it and sell it. So that's the thing about this. So this is a different unique design. Yeah. So that is all I wanted to cover regarding videos. So this is a sort of a summary of some things which we have done at IIT Kanpur. We are doing way more things. I mean, most of them are technical. What I have showed you is actually what is easy to look at in terms of hardware and actual flying vehicles. But eventually our goal is to build systems there. Whatever we do, I mean, our end game is to be able to make complete solutions, because like several of you, I mean, you get pained to see that India has not been able to realize its full capacity in aerospace domain. And how will it happen? I mean, if we don't contribute in that direction, it's never going to happen. Nobody is going to come and make India an aerospace superpower. And that kind of thing happens with small steps that we take by building small technologies here, proving these things, and eventually graduate to much bigger, much more complicated, much larger systems as and when, I mean, we have enough funding and enough opportunities for the same. So that is the motivation for doing all this. So we have, okay, I'll take a couple of more minutes before we close for today. So let's start looking at, I mean, the basic principle of a rotary wing flight or a VTOL aerial vehicle. So most of the VTOL aerial vehicles actually use a propeller or a rotor as the main lifting or propelling device. So the lift actually here is not coming from a wing. The lift is actually coming from a rotor, and this lift we call as thrust. So the vertical force which you get from the rotors is called thrust force. So that is the simple idea. But then, I mean, what is the basic physics here? So just like, I mean, all other aerial vehicles, here the rotor is generating the speed for the airfoil. So normally in an airplane, when the airplane runs, there is a relative speed of air with respect to the airfoil, and that's how you end up generating lift. So here the relative speed or relative velocity is generated by spinning the wing. Hence, there is a rotary wing. And in that process, the rotor actually pushes the air downwards. So rotor induces some velocity, which we call downwards, or which we call wave, or we call it slipstream. So this air is pushed downwards, and the reaction of pushing air downwards is applied on the rotor, where air actually tries to push the rotor upwards. And that's how my helicopter actually takes off. Does work on air by pushing it downwards and imparting a small velocity to that. And because the area is huge, right? So if my area is very large, so my m dot becomes very large. If my m dot is large, with a small v, I can generate adequate amount of thrust to make my helicopter lift up. So I hope all of you remember that analogy I gave you, where you can have a small control volume, and by just momentum balance, you can sort of establish the efficiency of an aerial vehicle, and also write the equation of thrust generation. Actually, you will encounter same kind of equations when you do any propulsion course. So basic propulsion course, when they start talking about rocket propulsion or even engine equations, you'll start by writing those kind of equations only. Now, when I want to maneuver, you have seen multiple videos. I just simply have to tilt my rotor tip path plane. Okay. My rotor tip path plane can be tilted in whichever direction I want, and I can go front, back, I can go sidewards, any direction I can fly. And that's why helicopters are called as the true, or rotating vehicles are called the true 6 degrees of freedom aerial vehicles. Vehicles which can fly in any dimension, any direction. Now, a conventional helicopter requires a tail rotor for torque compensation, or you require a second rotor. As you saw, there are multi-rotor concepts with other rotors spinning in the counter direction to balance out torque. So here is a small video, and I think we will stop after this video, where you can see somebody talking about how a helicopter is piloted.
What's even more awesome?
So here is a helicopter, which is a Robinson R-22 helicopter.
A quick look at the basic dynamics of helicopter flight. As we all know, there's one big rotor on the top to provide lift, and a smaller rotor on the tail to stop the chopper from spinning off out of control. But let's take a closer look at how they work. Each rotor blade is shaped kind of like the wing of a plane, but with two key advantages. Firstly, since it's spinning at high speed, it can develop lift even when the aircraft is hovering still in the air. Secondly, the rotors can tilt to produce more or less lift using this nifty bit of engineering called a swash plate.
Right. So this is the swash plate, and we'll look at another video of just swash plate to see how this swash plate actually works. So this actually has two parts. What you see here is actually the top part of the swash plate, okay, which is the spinning part, and there is normally a non-spinning part. So here, what you will do, you will put the collective stick.
Down here, where you might find the handbrake on a car, you've got the collective control stick. It's got a twist grip throttle on the end, much like a motorcycle throttle.
So it actually has a twist grip throttle. So just like, I mean, in your bike, scooter, car, scooter or motorcycle, you turn the grip, and that actually changes the throttle. It changes the engine RPM and it changes the power. Same thing is done here. So engine power is controlled by this throttle, which is there on this stick.
That controls the speed and power of the rotors. When you pull the collective upwards, it pushes the swash plate up.
So when
top rotor blades,
so you can see this whole thing actually tilts up, or rather moves up. So what he will do is, I mean, once he sits inside, he will actually turn on the engine, he will turn on the rotor. After rotor reaches a nominal RPM, that is the set RPM, then he will pull the collective up. And once he pulls the collective up, helicopter will actually lift off, like in this case. And collective basically increases the pitch angle of all the blades by same amount simultaneously.
At your feet, a pair of pedals manages a similar process at the tail rotor. Pushing the pedals alters the tilt of the tail rotor, which is spinning at a constant ratio with the speed of the top rotor. As you lift off, you need a touch of extra pedal on the right.
So the moment it lifts up, actually, the pilot will also operate a little bit of pedal, because what happens as I change the pitch angle, the torque, I mean, the lift is increasing. If the lift is increasing, my drag will also increase. And because of the drag, the power required by the rotor will also increase. So now, because the power has increased, so the tail, the anti-torque will also be, I mean, the requirement for anti-torque will also increase. And this requirement will be met by increasing the collective pitch of the tail rotor, which will allow you to balance the torque again. So he will operate the.
The main rotor.
So here also there is a collective.
You can use the pedals as kind of a steering wheel to rotate the chopper 360 degrees in the air. But the really interesting control is the cyclic.
This is the
control.
cyclic pitch control. So this is what actually allows you to fly the helicopter in whichever direction you want. So it's normally it will be the center stick or it will be a side stick. In this case, it is the center stick. So the center stick, I mean, whichever way you maneuver it, the helicopter is also, the rotor tip path plane will also tilt in that same direction. That is the whole idea.
Which effectively lets you control the tilt and acceleration of the helicopter in any direction. Here's how it works. Here's a top-down view of a helicopter in flight. In a stable hover, you can look at the main rotor as a fairly evenly balanced disc and lift. When you want to move off in a particular direction, you do it by creating extra lift at one particular point in this disc. And here's where we come back to that incredibly clever swash plate.
So this is this incredibly clever swash plate was invented by Juan La Cierva for his autogyros. And the swash plate actually allows you to manipulate the dissymmetry of lift, right? Because if I increase the pitch or decrease the pitch in a particular manner, I can actually manipulate the lift to go higher on one direction and lower in another direction. So the consequence of higher lift and lower lift is that wherever you have higher lift, the rotor after some point will actually flap up in that place. And wherever you have lower lift, the rotor will actually flap down. So the whole rotor tip path plane. So in fact, my helicopter. Okay. So the entire rotor tip path plane will actually tilt in a certain manner. Okay. So if I want to go forward, I'll ensure that my lift increases or decreases here rather. Okay. So as a result, this part will flap down and I'll increase the lift here so that my lift, this part will go up. And as a result, what happens? The whole tip path plane will tilt in this and the helicopter will try to go forward in that direction. So he will show that through some means also here.
When you move the cyclic control stick to
So
the
you
left,
see how the swash plate
plate
actually
tilts
moves.
so that the left side is lower
actually
and the right
moves
side
like
is
this.
higher. Now what that means is that as the rotor blades spin around, they flatten out and produce less lift as they approach the left side of the aircraft, and they tilt up and produce more lift as they spin around to the right-hand side. So the disc of lift becomes unbalanced. The whole helicopter tilts over in the desired direction, and you start moving at speed. Clever, huh?
Let's stick out to me.
So that is all in this video. Okay, so we'll talk about the swash plate in more detail, and we'll now dive into the basics of aerodynamics of the helicopter, and we'll also talk about some other research areas which are related to helicopters, which are still very open and require a lot of people to come in and contribute. So I think that is all. In more than 1 hour, I'll stop recording. Any questions from anybody? No questions?